So we're going to do a little recap, first of all, because we've covered the language section, we've covered the vision section, and there was quite a fair bit of material that we'd covered, so I thought it wouldn't hurt to go through and look at a bit of that. This is the last cohort sort of thing before we get to the presentations and then your project proposals. And yeah, so I didn't really get to the full recap. So we're just going to talk a bit informally, and I'll provide something later about like a bit of a write-up in terms of exactly what we've covered and what papers mean what. But just to go over it a little bit, Alana, did you have some starter questions you wanted to? Or not? No, okay.
We'd like to gain my office hours. Thank you. Yeah, I think we just wanted to like sort of think back on the sections, and were there any themes that stuck out to people? Anything that was surprising?
Okay, yeah. So perhaps we can open up to the class in terms of what themes did you notice throughout, say, the vision section in terms of what was repeatedly mentioned, what were the points that kind of slightly differed, or what are the general takeaways from the set of all of the vision papers? Can you sum up in a way? If you have to kind of write the summary of the course, yeah, Sanjay.
Like one of the things I noticed, it was like not only in vision or like NLP, but not even in this task, but it's like usually the authors are very focused on trying to prove that their number is better than somebody else's number.
Yeah, that's kind of normal. Yeah,
and they don't do the what do you call it, like the problem formulation and the experiment formulation correctly to like show that this is better because it gives us a more accurate model of the brain, maybe. But like this is what it explains how the brain is working. They usually go, this is 97% correlated. This is 63% correlated. It's like that's worse. That's better.
Yeah, in terms of the internals of what like the models they proposed and the methods that they use, is there anything? Well, first of all, that there is a similarity that you can use representations from vision models to map onto various parts of the brain, both in intracranial recordings in monkeys and using fMRI. Did you look at any image? No, we didn't, did we? And other things like this. But we'll say what particularly about hierarchy, for example, do we recall?
The middle layers being representative of the lower kind of visual cortex, and then like the higher layer of the models representing more of like the IT and the higher language areas.
What you began with, I think sounded a bit more from what we saw in the language stuff, where we had the middle layers were the best represented. But I think earlier on in the vision papers, we saw that it was more of a direct correlation between the lower layers to the upper layers in terms of going along the visual hierarchy from V1 all the way up to IT, for example. But then we also had a few different contrasting cases where we're using supervised learning, where we have a cross-entropy signal that comes back and constrains the representations in order to solve a classification task. And we did see that contrastive learning paper that said no, you don't actually need that signal. Just representing the visual statistics themselves is enough to derive a pretty good representation that can map onto the brain.
We kind of followed similar directions, using kind of simple type of models, and they were most of them they were similar. It seems like they didn't explore too much of how they can change the structure of the model or its architecture, or use other possibilities.
Yeah, I think the simple models definitely, because they allow they're more computationally efficient and train more of them, you get better insight into them. And I think potentially probably a few studies did look at other modalities but found they didn't work and didn't include the results because they couldn't figure out why. And that would be a natural question in terms of that. Did you have one of your hands up?
Yeah.
One of your
we typically averaged over the whole time series as well.
Mm.
So we saw things in more of just a single snapshot rather than how we might think an actual decision-making process might go.
Yeah. And then, when we moved to the language studies, we looked at recurrent neural networks and we looked at transformers and found the mappings onto the brain. Does anyone have anything they want to say about, say, context effects or anything like this? You presented a paper on context effects. What do you recall about this?
It's just about how the layers at first when I presented, I wasn't sure how what layers prevent what has on brain. But I think
That's the thing, nobody really knows this as well. It's kind of taking the results and then trying to infer backwards. What does it mean for the middle layer to become the most predictive of brain activity? And then we saw, say, in the recurrent neural networks where we had three, because the three recurrent neural nets, and the middle layer was actually supposed to be the more abstracted away from the stimulus, because as the stimulus comes in, it's in its word vector representation, and at the final stage, it also is. So there's kind of this curve between going from something that needs to predict an input, and then you have this ability for the middle layer to be more abstract, and that's the thing that fits it better to the brain activity. And then when we saw in the more large transformers with 24 layers, that there was the case that both as models became specialized for their tasks, we started to see, in terms of potential overfitting, that the brain activity predictions came down at the end, and it was mostly the middle layers that held this representation. But also the fact that iteratively building up context and just showing that word embeddings have a correlation in the brain to a specific area, but then actually showing that how they're combined together in language models also meant that we could link that to various places in the brain that we know monitor context and long-term activity. And you can see that in, say, in Henry's paper, for example, but seeing the visual word embeddings, CNN embeddings only being active around 100 milliseconds at the back of the brain. Then the bottom layer of that transformer fixed embeddings was like the word representation, the lexical representation that doesn't have any context. And then with the transformer ones, we just saw that after even up to about 1 second after those broad red predictions, I can just visualize the animation you showed.
It does make me think that that was sort of like an attempt to find the hierarchy that is in the CNN in the brain. So it had to go to these sort of clunky set of instances in order to find that hierarchy of information processing. Will we ever get something better than that? Will there ever be a transformer where the layers actually correspond to some sort of hierarchy of language processing?
Potentially if they're coerced into being more brain-like.
Okay.
Yeah. I was going to say maybe, but will it perform better than?
Yeah, exactly. Is the purpose more an engineering outcome, or is it to use the model as an in silico replacement to give it language tasks and see how it performs as a model, because it's so expensive to collect brain data? And yeah. But okay, is there anything else we should really say about the recap? Or
I guess I really enjoyed the control papers in the language.
yes. So the two papers that Laura presented in terms of actually being able to use a model to directly not just predict an association, but then causally refer back and create stimuli that would drive the responses either up or down. Yeah.
It seems like in this class that's what the general trend is so far, is trying to shift from correlation to more causal models, causation. Is that reflecting what's happening in the research community right now in this field?
To a degree, I think there's still a lot of correlation research because there's still a lot to kind of find out. I think it progresses in terms of, let's find the association first and let's see, how good is this association? So first of all, the step, it wouldn't be that, to just, before a correlation set of results would be found, I don't think you would imagine to go directly in and start trying to modulate the activity. You sort of need to establish that it's there first, and then that provides the way to, okay, then now can we control it a little bit? And but I think as we go forward, we're still going to see quite a lot of correlation research. But this is, as we have better models that can learn better features, we haven't been able to, say, correlate them to more smaller areas of the brain and regions of interest. And so I think there's a lot of scope for correlation research going forward there, and then also as an offshoot of that to see whether that can be modulated and find that causal relationship. Okay, let's get to reinforcement learning then. The three main domains of machine learning: unsupervised, supervised, and reinforcement learning. Is anyone sort of not clear on what each of these three mean, or would benefit from a small sort of statement? So in unsupervised learning, we don't have any access to the labels. We just look at, say, clustering methods, things like k-means. And in supervised learning, we have labels. We want to learn decision boundaries, or we want to learn generative models of the data, and then work out for which class is the highest probability. And then in reinforcement learning, we have this different setup where we have agents and environments, signals, and just a fundamental different type of machine learning that's very much made its home here in Edmonton. So yeah, in reinforcement learning, we have agents, actions, rewards, and observations from the environment. This is just a very broad setup. So a better example we have here is the car. So a car, if the car is treated as an agent and it's on a road, for example, the road is the environment, and we're getting signals from sensors, they're coming in as well. And we have an internal policy function which needs to take in the percepts, the reward from previous time steps, come up with a reinforcement learning algorithm, and then suggest what action should we take based on the current time step of what we're actually observing now, plus what we know in the history, solely to maximize the expected future sum of rewards. And in reinforcement, we have an environment, we have a reward. It could be, in terms of the psychological research, we often would pay, participants some money if they get things wrong and study this. But say in more machine learning approaches, it's more of an abstract scalar signal. And we have an agent, which is typically modeled as a neural network. And then we train the agent, and once we have the final agent, we can plop it into a robot, or use it as a more abstract system here. So today we're going to talk about how the brain learns the dopamine reward system, a particular event-related potential called the error-related negativity. One study on how this combines in with the dopamine reward system. Then we'll look at an explore-exploit fMRI study, some other comments on brain RL papers, and then sort of where we're at, what's in the future, and where we might go from here. So we're going to start with neurotransmitters. So learning happens at the synapse. This is something that you would often hear said in a biology course as well. So if you have two neurons, the gap between them is called the synaptic cleft, and what will happen is an electric signal that travels down the axon and then promotes the release of chemicals. So these chemicals, neurotransmitters, a few other things as well, in these little bundles called vesicles. These then propagate down to the end of the synapse and then are released into the synaptic cleft, where they bind to receptors that are on the postsynaptic neuron. And this process happens. And as this happens, you allow the intake of various the chemicals that go in that change the potential between the inside of the neuron and what's going on around the neuron in the extracellular space. So once that's modulated, you can sort of have the microvolts. So things are usually sitting around like microvolts as well. But once you allow some positive or negative chemicals to come in, this will then change that. And then once you reach a specific depolarization threshold, this then promotes the neuron to fire down its axon terminal. And so all of the connected neurons in the brain flow like this. But one thing that happens here is more receptors can be built in certain cases. So when you have firing of both one neuron that leads to firing in another, this promotes a link. So it means that there's a more dense population of receptors. It means it's more easy for certain transmitters to be able to attach from one to the other. And so we have a few different neurotransmitters here, probably a few that you've heard of already. And these all have primarily associated behaviors in the brain. So at the top we have serotonin. If you know anything about antidepressants, there's the class of antidepressants called SSRIs, which is selective serotonin reuptake inhibitors, which if you just look at this Simpsons cartoon at the end, you can see after the neurotransmitters are in the cleft, then there's a process to reuptake them back in and then repackage them into vesicles. What SSRIs do are they block the reuptake procedure. So it means that there's more serotonin in the synaptic cleft, and this promotes feelings of happiness and has a connection to targeting depression. And we have cortisol, which is associated with stress and does not spark joy. And so adrenaline, you might have heard, it's like a fight or flight neurotransmitter. What else do we have here? We have serotonin, dopamine, glutamate, cortisol, GABA. The one we're going to look at today is dopamine. I presume you've all heard of dopamine, and you are aware that there are connections to happiness and pleasure seeking as well. It's often talked about in the literature today, kind of slightly incorrectly in terms of what social media companies are doing, for example, in terms of the like button and notifications. a lot of stuff comes out to say that they're specifically trying to target the reward system and have us hooked on social media. And there's a lot of psychological research that how can you design interfaces with the public that promotes the release of dopamine and this feeling of like an association that you would want, a behavior that you would like to repeat as well. So if you are aware of reinforcement learning, this comes in to those ideas as well. So there are two places in the brain where dopamine is created. Two main places anyway, the ventral tegmental area and the substantia nigra. We'll talk about the substantia nigra on the next slide as well. So here's one slide from this Guardian article about dopamine and Facebook and all things like this as well. So the attraction triggers the VTA to reward the rush of pleasure from the neurotransmitter dopamine. And then also we have the substantia nigra. So this means black substance in Latin. So when they were doing postmortems, for example, they were trying to map out the areas of the brain. They just noticed there was this area that was black, for example, so just call it the black substance, and that name stuck into modern terminology today. The substantia nigra is what is damaged when people have Parkinson's. So we're going to see a lot of connections to dopamine and downstream motor effects. And I'm not going to look at the disorders, for example, but the breakdown of dopamine that promotes the motor system has an effect on, people who suffer Parkinson's have an inability to have good control over their own actions, and this is due to things that are going on in the substantia nigra. And so, like the VTA as well, it also sends the dopamine reward signal forward to different parts of the brain or up onto the cortex. So why would we need to consider dopamine as a reward signal? That's a very, very valid question. And so basically it comes out of these studies in the 50s, which we're going to talk about later, and rats. But basically the brain's idea is it wants to learn behaviors which stimulates the release of dopamine. Anything that you could do to enhance the ability to have a dopamine release in the future, you would want to update the probability of repeating those actions in order to get those reward signals coming through to the brain. This also has implications for addiction, and in obsessive compulsive disorder, we know that the reward system has gone a bit haywire in terms of what's going on here. And the complex reward system, the observations that we had in sort of animal studies then sort of had a role in developing reinforcement learning. I think this was kind of an idea that was going on ahead, and then once the associations between the two fields were established, this provided a lot of ability to test theories and try to work on algorithms that would be better brain-like. So in terms of the whole course machine learning in the brain, we've seen quite a lot of direct mapping between neural networks and the brain as well. But more at a fundamental level, reinforcement learning is the sort of original stronger connection in terms of seeing what's going on with dopamine and the reward system. I hope this plays. Oh, this video is not available. Why? Going to be able to get it. This is just a short 1-minute video that kind of described what we're going to talk about in a little bit. This 1950 study of rats. So I'll just try and have to explain that one from this slide as well. So in 1954, Olds and Milner had this study where they placed electrodes that promoted the release of dopamine in rats, and they found that when a rat would press the lever, there would be a hit of dopamine, and the rats became pretty obsessive about it. They would not eat. They would only want to consistently just go and press the lever and have the dopamine release and sort of forget about all of the other behaviors that would be typical in rats as well. And this led to what's called the dopamine hedonia hypothesis. So hedonia just means pleasure seeking. And this was the first idea to say the release of dopamine is in some sort of reward system. And so one of the proponents of this dopamine hedonia hypothesis is Roy Wise, and he said in 1980, that dopamine junctions represent a synaptic way station where sensory inputs are translated into the hedonic messages we experience as pleasure, euphoria, and my favorite word, yumminess. Then, for a few years go past, and people are still trying to figure out what's going on in this dopamine reward system. Then we get to a series of experiments by Wolfram Schultz in the early 90s and mid to late 90s as well, where he started to say, okay, dopamine is not actually a reward signal, it's doing something else as well. And so there's a quote by somebody else about Roy Wise that in that same year is one of these influential studies that we'll talk about in a second. And then he says, I no longer believe that the amount of pleasure felt is proportional to the amount of dopamine floating around in the brain. And the most recent quote in 2008 was that pleasure is not a necessary correlate of dopamine elevation. So we'll get into what all of this means now. But basically, it's connected to the idea that it's not the reward signal itself that dopamine is controlling, it's reward prediction errors. So the original hypothesis, according to the dopamine hedonia hypothesis, would be that dopamine release is concurrent with reward timing and signals of pleasure reward. So this is what Roy Wise was saying in 87. But yeah, afterwards, we know that there are some experiments where they introduced the idea of a reward cue. The reward cue you might be familiar with from Pavlov and his dogs. He rings a bell, this salivation. Through learning, the dogs associate the bell with the presence of food, and then we know that they are expecting food when they hear the bell. And then, or also, this little cartoon here that says, as soon as I drool, Pavlov draws in his little book. Yeah, so the idea of a conditioned response with a cue that is a signal of reward is more connected to what we see in the experiments that Schultz had as well. So we have three different things going on here. At the top, there's no conditioned stimulus. This is a raster plot. So this is like that, saying that whether a neurons over a set area in a dopamine area is active, and at the top you have the histogram counts of there. So the higher, when you see a peak, you just see there's a higher density of neurons firing. And yeah, it was in one of this. So there's no conditioned stimulus. Then all of a sudden we present a reward here. And once that reward is presented, there's a shoot up in dopamine. So this is the same thing that Olds and Milner saw in their rat experiments, and it led them to think, okay, we present a reward, there's a boost in dopamine. Dopamine is the signal of reward. Then, with the conditioning of a stimulus, so slightly before and after some learning by the monkey, what happens is the conditioned response expects a reward, because obviously it's a conditioned response with like the equivalent of dinging a little bell, and we would expect a reward to come later on. And there we see the spike in neurons and dopamine neurons. And then the reward is presented a little while later, and everything seems sort of standard. We were expecting the reward, and we received the reward. In this last version, there was a prediction of reward at the conditioned stimulus. So the condition was given to the monkeys to say a reward is coming, but then we don't actually present a reward. And what we see is a very systematic low firing, or virtually none. You see nothing in the histogram. So this is a signal to say, okay, I was expecting a reward, but it didn't arrive. So these dopamine neurons have a role to say about something about expectation, or what we're going to say here is reward prediction errors. So when we don't have we're not expecting a reward and we receive one, we're happy. When we are expecting a reward and we receive one, we're also happy. But then when we're expecting a reward and we don't have one, we're quite unhappy. And so this is the signal that was hypothesized to be the correlate of what we can call a reward prediction error. The reward prediction error is, we can define it as the actual reward subtracted away from the expected reward. So if we see here, then we were not expecting any reward, but we did achieve one. So this one in red, so the actual reward we received subtracted from what we were expecting, which is nothing. We have a 1 here, so this is saying that we're happy. We need to update our values to say that, okay, whenever we have this environment that we're in, this particular setting of state, there could be a reward coming as well. In this case, because a reward, all the monkeys were expecting a reward and they received one. We were expecting both. We don't have anything because, like I say, it's a reward prediction error. There was no error in this case because what arrived was what was predicted. But then when there's a case of actual reward minus expected reward, then we have a negative signal to say, okay, there's something else going on here. We need to update this because this Q that we've learned might not actually be representative of a reward in the brain. So the earlier hypothesis that dopamine release is concurrent with reward, that sort of goes out the window. And then the emerging view after this in Schultz's work says that dopamine release is concurrent with reward prediction errors. And what are in here? When we don't make a prediction but receive reward, negative prediction error. Yeah, so this just says that the release of dopamine, it's not just about the conditions of having conditioned stimuli and rewards. You know, you don't have to be doing anything. You could be in a novel environment, and you know, if you walked into class today and I gave you $1,000 each, you'd be okay. You know, I need to come to class more often because, like, you know, this could be a thing that I get some reward from. But so it's sort of an ongoing active part of not just a specific scenario of sitting in a lab and having a monkey do something, but more of a general, consistent brain basis of predicting environment. Yeah.
Do we know, so like on the last slide, where you had all the dopamine levels, do we know?
This one?
Yeah. Do we know why? Because, you know, you can kind of think why dopamine would spike on the response, right? Because you're expecting it, so it spikes, right? But do we know if there's like a learning reason why the dopamine spikes?
When you are learning, what you see in the middle one here, when you are expecting it, you don't get the dopamine on the reward. It's on the conditioned stimulus that's predicting the reward beforehand. Does that change your question?
No, it's still just like so we get the dopamine on the prediction stimulus, and then I guess it's like normalized by receiving the award at the same time. Like,
You mean why is there no effect on the presentation of a reward? That might be a fluctuation in this graph.
mm-hmm.
I also had that question a little bit. I'm not 100% sure. I think that if dopamine is purely the signal of a reward prediction and you don't receive, you know, this, what we're going to see a little bit later on is there's another factor to this in terms of the timing of the presentation of reward as well. So that's also going to come into play. And I think if the timing would have been extended or not, there might have been a bit of a difference here. But in terms of what's going on, because you can make that disassociation between the presentation of the reward, if you're expecting it, it doesn't matter whether if there was dopamine or not, because that's not driving the signal. You know, you already made your prediction, and as long as there's nothing to update, we're going to see a few brain areas that are kind of constantly monitoring this. And you know, if there was like in the last case, something that needs to be taken, there are areas that would integrate and send signals back again to say, you know, we need to unlearn the conditioning of the stimulus.
I've actually had a question about that. So the bottom plot there, and don't we have like a positive reward prediction error and a negative reward prediction error?
Yes. So perhaps a reward prediction error. So you can think of the positive reward prediction error as being, I have this written up in a few slides later as well, but as being just like the amount that you need to change. If you have a prediction of the system and you know you have more reward as well, then an error that's positive means that, yeah, you are not predicting. So basically, only in the middle case are you actually making the prediction and it's coming true. In the case of not expecting a reward and receiving one, or also expecting one and not receiving one, you just have offsets, which it's kind of like we're going to see that connected to temporal difference learning and TD errors, where you know you just need to know by what amount and what sign to make an update in order to have a better prediction of the system. Does that make sense?
Yeah.
Cool. So there we are. So the paper that we're going to look at in a second will point out the connection between dopamine and temporal difference learning a bit later on. And also point out that the neural network models that use this adaptive active critic model, I should say, to output a temporal difference error when the prediction changes. Yeah, so the TDR is positive when the reward is better than expected. TDR is negative when the reward is worse than expected, which is also the case in the case of an absence of expected reward. We'll select the actions to reinforce behavior that elicits that reward. And then if you have a TDR, this then needs to propagate back from the moment of reward or lack of reward to the conditioned stimulus in order to make sure that we're constantly monitoring the relationship between did we get what we were expecting or not.
I was very excited after talking with Peter about his.
We know that dopamine release increases in response to anything good happening, like getting food or money. But receiving any reward is also inextricably linked to reaching out to it or somehow moving towards it. We trained rats to press a lever for a reward. We then trained the same rats to stay in one location for around 2 seconds in order to obtain the same size reward. And we recorded dopamine release while the rats were either staying or going towards the lever. When rats hear the cue to go to the lever, dopamine release is immediately increased in a part of the brain called the Nucleus Accumbens. The bigger the reward they're expecting, the bigger the release. Interestingly, when they hear the cue to stay, no dopamine is released in the Nucleus Accumbens until they finally move towards their reward. So what we've shown here is that dopamine release is strongly affected by whether or not we move, which
Accumbens a little while in its role in action selection and movement. And this is one of the things of the conditioning stimulus, that even though there is a prediction, in some parts of the brain, the dopamine neurons will be firing, but only if you're kind of taking positive action towards attaining that goal. That's where they've recorded the information in the rats. I think it was rats. That is when you see triggers of dopamine that are connected to action selection. So yeah, in the Nucleus Accumbens, we have, it's where people have suggested that we have the monitoring of motivation and action, and also many more different reward and pleasure-seeking behaviors here. So it's still under the cortex. It's close to the ventral tegmental area, just projected a little bit forwards. And one of the first stops that the dopamine train is on after it leaves the departing station. The Nucleus Accumbens is part of the striatum, and its connection to reinforcement learning is that there are, where value is calculated and actions are selected, and where you can monitor feedback signals if you should take different actions for different rewards. And yeah, so many of the dopamine pathways would lead through the striatum, particularly the Nucleus Accumbens, but also to other areas. And its role is to keep track of the state and action values and then integrate over them in terms of kind of being a monitoring station, and based on the information of what's known from prediction, expected error signals, we then select the best action, send it back to the cortex, so then up to the motor area to send the command to perform whatever action has been learned in order to predict the reward. So here's a little schematic of the different areas of the inner part of the brain and the relation to reinforcement learning from this paper in 2000. I've made a little change here because I think in later research in the last 23 years, people now probably wouldn't say that they would say that the striatum is actually the action selection area, not the pallidum. So, and reward prediction, it's all a little bit more complicated that, but the point I wanted to say here was that you see this grey box, the dopamine neurons, and this is going to be representative of this temporal difference learning signal, which is the difference between expected and actual reward that comes from reward prediction errors. So we're going to look at this paper by Holroyd and where is it all? Holroyd Coles, that's right. So 5 years after Schultz had his monkey experiments that we saw with the raster plots and the histograms on the top, there was an observation that is connected to what we see in EEG, connected to monitoring errors. And so after Schultz's research, people have started to say, okay, we actually think this is going on in reinforcement learning, reward prediction errors, dopamine system. But then the people who are more interested in the cognitive neuroscience, they know, okay, we actually are aware of quite a lot of monkey research in the 70s and leading up to research in the early 2000s that there's an EEG signal that's detected whenever a participant knows that they've committed an error. And so the goal here is, we propose a hypothesis that unites the two accounts by linking the generation of this ERM, which is the event-related negativity, to the activity of the dopamine system. And we suggest that when human participants commit errors in reaction time tasks, the dopamine system conveys a negative reinforcement learning signal to the frontal cortex, where it generates the ERM by disinhibiting the alpha dendrites of motor neurons in the ACC. The ACC is the anterior cingulate cortex as well. Again, right in the subpart of the cortex as well. It's the frontal part of the singular cortex, which just sits over the corpus callosum that connects the two halves of the brain. And this is being implicated in processing of rewards, anticipation of rewards, and where intentions are transformed into actions. And as you might remember from a few slides ago, there's quite a few different places in the brain that people have said are responsible for action selection. So it's not really clear, and it's the emerging consensus does change over time. And yet we're going to come back to the anterior single cortex in a little bit. So do you remember we had our coding workshop where we looked at the N170 response to faces? We had presentations of intact faces and scrambled faces. And when we looked at the difference, so the collective response to scrambled faces versus the collective response to non-scrambled faces, there was an effect, negative potential around 170 that had been interpreted and is a signal of face processing. So that same idea then, when we went to talk about the neuroscience of language, we saw the N400. Remember this Harry Potter expertise thing in expectations and things that are semantically linked. If we're not expecting them, this gives a rise in, the drop in the negative potential. And also we mentioned P600 a little bit. It has connections to syntax, but isn't primarily 100% a syntactic ERP. So what we do here, we have a stimulus, we record it, it goes to the amplifier, and then we average the signal across a few different conditions. And then we can contrast two different conditions. In the case we're going to talk about with this event-related negativity, this is between when the participant knows that they haven't committed an error versus when they have. And the hypothesis is that this is generated in the anterior singular cortex approximately 50 to 80 milliseconds after awareness that an error is being made. So this just says this here. So we have the blue here just represents the negative part of the dipole in the brain, and we have a contrast thing where the solid line is what happens when there's an error versus when there's a correct action. And you can see, as I mentioned last time as well, there is this work where in older EEG research, negative is actually pointing up the y-axis rather than down. So even though you are seeing a positive speak, that is more negative activity. So how do you elicit the ERN in an experiment? So one common thing to do is what's called the flanker task. So the flank just means side. So in a case like this here on the right, the goal that the participant wants to do is to press either the left or the right button, depending on what is going on in the very central direction arrow. And because we flank to the left and we flank to the right, we can have stimuli that are congruent or incongruent, and this increases the likelihood that an error might be made. There are a few different ways. So if you want to study when humans make errors as well, if you have an easy task, people know what they're doing as well. You need to make the task difficult enough where you might be able to catch quite a lot of unintentional errors, because of conflicting stimuli, or if you ask them to do it at a fast pace, you could press them to go, oh no, I shouldn't have done that. And this is one of the things that you want to be able to record. So when the participant presses the incorrect button, we also see the ERN, even when the individual is not aware they've made a mistake. And here's another important point, that the size of the ERN is a direct reflection of the cost or value of the error. Now, back in that short video I showed you as well, they also mentioned this in the dopamine system as well. But there is this link between, it's not just capturing an error, the size of the magnitude of the error that you record, whether it's dopamine firing or this event-related negativity, it's directly correlated to the cost of the error as well. So if you have two sets of people who are taking this test, for example, and if they know that, usually you would start off and say, okay, here's $100. Every time you make a mistake, you're going to be deducted by something else. So the magnitude of the cost of making an incorrect error for the group that has a higher deduction, so whenever they made a mistake and then, oh no, I've just lost $5 compared to like one, you see that the size of the ERN correlates pretty well. So whatever the subject experiences, if the cost of making that error is connected to the size of what we see in this event-related activity. Because this has been known for quite a while, and people have tried all sorts of different combinations of how to give answers in this, or how to present the answers back. So it's like people have given the incorrect stimuli by pressing foot pedals or by doing something crazy with their eyes, for example. and then also presenting the feedback, just in order to get a broader sense of, okay, could this be correlated to like, the presentation or of feedback? You want to try and be able to say, okay, we see this effect no matter how we present, how we have the participants signal their response in the task, or also how we present. So even in terms of saying you have 2 taps on your shoulder to say you've made a mistake versus like 1 to say that everything's fine, or no, you make a correct prediction, and you always see this ERN. So it's a very generic signal and high level because of this as well. And yeah, because we knew about this from recording in monkeys done from the 70s, which was about 15 years before the advent of fMRI in the early 90s.
Yeah, so you have in here that it was correlated directly with the amount of money, right, that was taken away. So was this like if somebody was given $100 and they, like, I'm assuming this is for one error they got $5 taken away, for another error they got 10, like more and more amounts. What about when like one single individual was only ever punished $5 and then a different individual was 10? Would they still sort of know proportionally that the 10 is worse, even if they were only ever taken, like even if they were only ever punished by taking away 10 versus another subject who was only ever punished by 5? So,
I think that's connecting it to say what else might be going on in the same experiment. But in terms of what we want to hear, it's your own subjective. It's not about what's going on in somebody else. So you would take different groups of people, put them in one at a time, and for each group of, you'd have differing costs of making an error, and it would be aggregated at the group level. Sort of, I'm sure there have been studies where it's maybe gradually increased the more mistakes they've made. I'm not aware of those. Typically, it's just a kind of, you have group A, you have group B. Some have a very small deductions for the cost of making an error is less, versus a larger group. Contrast those and see, okay, for the group that had the larger cost of making an error, they have a higher ERN.
okay.
So the fundamental idea of this paper was to unify what's going on with the ERN and also the reward system, dopamine reward system hypothesis. So the idea that they wanted to put forward was that dopamine signals start in the ventral tegmental area and the substantia nigra. They pass the signals on that dopamine train to the anterior cingulate cortex in order to update the predictions, and once the dopamine arrives, if an error is inconsistent with the prediction, so there's a belief that an error has been made, this is what generates the ERN approximately 50 to 80 seconds afterwards. So how they tested this was they first took the idea that they know that the ERN can be elicited by negative feedback and also error commission. So when you have fast tasks where, because of the speed, you might make an error, you might instantly know it, or also by having confounding stimuli, like in the flanking task, this is error commission. You see the ERN at this point as well. But you also see it when you have negative feedback, because let's say you have, you believe that you've made a correct decision according to the task, but the signal comes back negative. You also see it there as well. So they wanted to combine what's going on in both of these. So how they did this was they had 6 stimuli, 10 blocks of each with 300 trials. And the goal was that you would need to press left, you would need to press right, depending on the image. And these would kind of rotate around different blocks. So the trial structure here is randomly on each block, 1 image would be associated to press left, 1 would be press right, 2 would be associated to the condition where it didn't matter what the subject pressed. They were 50% reward or 50% error. And in the final 2, again, it doesn't matter what the participants pressed. They would always either receive a reward or not receive a reward. And by modulating those conditions and measuring the ERN, they wanted to evaluate whether the proposed computational model could be a good predictor of what was going on. So in this first case, let's go back. Yeah, so we have this 100% mapping, which is the first 2, which means that if it's mapped to left and you press left, you get the reward. If it's mapped to left and you press right, you don't. So there's actually a signal that can be learned here through observing what you've done for that image and what the feedback was, and for the others, not so much. So in the 50% mapping, this is, again, there's nothing to be learned in this case. It's just an association to whether you get feedback or whether you don't get feedback. And so because there's nothing to be learned, feedback can't be predicted. So if you remember from when the monkeys were learning the conditioned stimulus, like when there is something to be learned, that dopamine signal in that case as well, which it was shifted back to the point of the conditioned stimulus, and then that is the effect of learning what's going to happen. When you can't actually do that, you have to wait for the feedback. So they had a computational model that predicted that in this case, there's nothing to be learned. So you would see the ERN for mistakes that they've made. So the black bar here is the actual recorded thing from the experiment, results from the experiment, and then the one with the striped lines is what their model predicted. And further along, we see the ERP recording to show that there's a difference there. In the case of the 100% mapping, there is something to be learned. And so again, like we saw that shift from dopamine release, because the idea is that it is the release of dopamine that sends the signal to the anterior cingulate cortex, that because if you see a shift in the release of dopamine, that would also mean there's a shift in the ERN, which is what they do find here. So after those two images where they had learned this image means I press left, or because it's the clock, I press right and I receive a signal here. Then the way that you have to measure this is because they're getting it right, but you want to measure the error. This is because of the speed of the presentation, because they had quite a fast rate that, you know yourself, if you have to do something really, really fast and you know what you're going to two piles, or maybe to press a button, for example, because it's so fast as well, you can say, and instantly you know, okay, that was the wrong thing to do, and then that sends the error signal. So this is what's being recorded here, that the errors for the response, when they knew instantly they made a mistake, had started to propagate back to here because there is something to be learned in the signal. And in the final case, there's nothing to be learned, but also the feedback can be predicted because you always know if you press this button, you always get a reward. Or if you press this button, you always get a, well, not reward or a punishment, as they say. And in this case, there's not really any difference between them, or no statistical difference. So the idea that they end up here with is just to say that because they were able to take the previous results from the monkeys and the dopamine system in terms of the shift of reward to continuous stimuli based on the idea of the event-related negativity in a probabilistic learning task, that then linked very well to modulating the expected changes that you would see in event-related negativity. And this was the hypothesis that they claimed that they had said that the ERN is directly driven by projections of dopamine from the VTA and SN all the way through to the anterior cingulate cortex. We're going to shift a little bit to talk about learning the brain back at the synapse level, but does anyone have any questions beforehand or anything to clarify? Nope. Okay. Who's heard of this before? Cells that fire together, wire together. Yeah. And it's, but how do you understand it, Jay?
Just like neurons in your brain that are used more constantly, they are more linked together, and like if one fires, then it's more likely that the other one will fire as well.
Yeah. So this is what we saw a few of at the beginning with the blue neurons and what happened in synaptic cleft as well. So yeah, the idea is here that when there is concurrent activation of presynaptic neuron and the postsynaptic neuron, then the receptors are connected, which means that they're more easily triggered by the release of lower levels of neurotransmitters that presynaptic neuron. So here we go again. So the presynaptic, synaptic gap, and the postsynaptic. And so here are the vesicles containing the neurotransmitters, and in blue we have the receptors on the postsynaptic neuron. So this Hebbian learning, as they call it, the Donald Hebb, is connected with two-factor learning. So basically, as Jay pointed out, if you have concurrent firing of both neurons, then there is a connection there. So yeah, this is what's called a two-factor learning scheme. So at the top, what we'll have in green is the presynaptic neuron firing, and secondly, in orange, the postsynaptic signal as well, which comes slightly later because obviously things take time to cross the synaptic cleft. And so we can either see activation in the presynaptic neuron followed by bursts in the postsynaptic neuron, or more of a sustained activity. And this both, realize the same thing. So what you'd want to do is when you had concurrent firing of both neurons is to consider this updatable. So the Hebbian one that connects the weight between neuron I and neuron J is that it's based on what's going on in the presynaptic neuron and what's going on in the postsynaptic neuron. But Hebb's rule is incomplete. So we're missing something here because where have I taken this one from? Yeah, so a wealth of evidence supports Hebb's rule, but researchers realize that the rule is incomplete if the aim is to select an appropriate action, because the rule is ignorant about the usefulness of that output. So, many times we're making mistakes in life and, neurons are firing together, but they don't actually benefit us in terms of predicting any reward in the future. So just because neurons are firing together does not mean that that was necessarily the right thing to do. So we're missing one thing here, and I'm guessing you can figure out what it is. What does it say here on the right? The influence of theories of reinforcement learning increased tremendously when it became clear that neuromodulatory systems, such as dopaminergic system, code for unexpected reward. And this gives rise to RPEs. So what we have now is the extra factor, which is error signals. So considering what we had before, firing of the presynaptic neuron and the postsynaptic neuron, and then obviously there's no signal here. And in this bottom case here, we have the same thing again. We have a temporal gap between when the dopamine error signal would arrive. So those are the three factors that are needed to model the learning in the brain that actually encodes useful things that can give us feedback about whether our actions are useful or not. So if you look at this mouse here in this little maze, we're going to talk about eligibility traces in the brain and how neurons can be updated based on these signals. So if you imagine, place representation over in B, we have active and inactive neurons, and these represent the mouse's understanding of where it is at the moment. And then the mouse can either go left or it can go right. And this represents what's called the action plan over here. And so we can go left, we can either go right. This isn't the best labeled path because when this is presented in slides as well, they change the colors and they move things around, but that's not what's in the original paper. So let's say that the mouse decides to go right and then selects this plan. Then we have active neurons that go there. So the concurrent activation of both, this sets up what's called a synaptic flag. The synaptic flag is basically synonymous with eligibility traces in the brain. It basically says, because both of these neurons were active at this moment, I am eligible for any update that comes back if a reward signal is given. So let's say the mouse goes over there, over to B, doesn't find cheese, and therefore there's no success signal by going right. And then it resets, or goes back to the beginning again, and that's it. Now shifts over. So imagine some of these white circles become inverted with the other with the shaded version, and then we select the action plan to go left. Send those motor commands to the motor cortex of the mouse in order to go left, and then find the cheese. The cheese is the the reward signal, because the motor plans that were mixed in from the place representation, they have now this synaptic flag that says I'm eligible to be updated. The reward signal comes in from the cheese, and it just means that those weights can be updated as well. So kind of systematically represented in C, where we have pre-neural activity, post-neural activity, we have a small gap, and then a success signal will come a little bit later on. This was a plot from some reading that we suggested prior to today, but I think the previous slide explains that a lot. Just to go into some detail about this, these flags and eligibility traces. In this case here, we have the postsynaptic neuron. So remember, green is always what's going on in the presynaptic neuron, and orange is the second factor here, the postsynaptic neuron. So we have connections here, and we also have firing here. Then this signal propagates forward to this neuron here. So this is a synapse, this is another synapse. We have activity in the first synapse, but then there's no activity in this one as well. So then what happens is, only because there's coincident activity propagating forward, we have this flag here, which means I am eligible to be updated if a reward signal will arrive. And then later on, we have this reward signal. And this means that as the error signal is propagated back, only the neurons that were tagged as eligible to be updated are changed in weight. So there's also an aspect, I think you mentioned about the timing, or that was my answer to what you said before. So it's not always the case that you can just present the dopamine exactly at the exact same period as well. So people have set up conditioned stimuli in animal models and animal recordings actually, and then presented dopamine at various delays afterwards. So after you have the presynaptic and the postsynaptic neuron firing, then what happens if you change the time when you present the reward signal? And as you can see, the proportionality, the weight change, diminishes the later that you present it. So what happens is that these eligibility traces will fade away after a certain amount of time, and that means that once they faded away, there's no signal to say, okay, if there's a future dopamine thing, that's all sort of forgotten about as well. But there is an odd thing here that differs in reinforcement learning models where dopamine is linked to the TD signal, that even if you present a reward slightly before the neuronal firing, the eligibility traces in the brain and those updates, they're very strong. They're actually the strongest that you will find afterwards. So that's something that's pointed out in Sutton and Bartow book as being one of the major differences between differences in reinforcement learning in the brain, with this connection of the dopamine reward system and reward prediction errors. I'll just introduce two brain areas because they are going to come up in this next study we're going to talk about, and also in Sam's presentation on Thursday. They will also play quite a role there. So first one is this intraparietal sulcus. So we have the parietal cortex and intermediate between. The sulcus is the not gyrus. And so you can see it's highlighted in red there, that small period. And then the lateral prefrontal cortex, which is this huge area at the front of the brain on the side of the brain, the left side, yeah. And so the IPS is connected with motor planning and motor control. And the LPFC is decisions planning executive function. There's not many things that haven't been implicated in the prefrontal cortex, to be honest. So you have to be careful of that. One thing that is also relevant to reinforcement learning in the brain is the idea of the explore-exploit trade-off. Does anyone want to take a stab at explaining to the class? I know there's some reinforcement learning expertise here. Srinjoy, yeah.
So to exploit means to whatever policy we have, which we are using to find the best way of moving through whatever problem we have, is to use that policy and exploit it. But to find the good policy, we need to explore the environment to actually set those values. So we need to, in some steps, we need to take steps which are not the best and then try to see, oh, let's see, suppose in chess, let's see the best move is knight to somewhere. But then let's see if I want to move the pawn and what happens. Maybe I win, maybe I lose. And depending on that, I would decide, oh, the pawn move was a bad move.
I could not have come up with a better explanation myself. That was great. So yeah, what actually happens in the brain when people are exploring or exploiting, and what kind of networks do we see? So this, they took 63, like these mid-level managers and people who were, proclaimed to be good in business. It was kind of a business-related paper where they were looking at what was going on in the brain to inform some sort of decision. But it has a lot of relevance for looking at the networks that are active when we do exploit versus explore. And so, yeah, there's a connection between attentional control and also reward tracking. So these are the things that are repeated quite a lot throughout this this paper. And so they state that the exploration requires disengaging from the current task. So when your task is to maximize the reward that you have, you need to disengage with that and start to kind of control what else could be going on in different areas in order to allow me to explore, like Srinjoy said, in terms of being able to potentially explore the space and find better rewards. And yeah, what happens as a task switch happens as well. So there are three hypotheses this paper puts forward that says that exploitation, like compared to exploration, will involve stronger activity of reward-related brain areas. And hypothesis 2 says compared to exploitation, exploration will involve stronger activations of the reasons of assessment of reward-related uncertainty, because where you're uncertain, the most might be the place where you want to try and explore. And hypothesis 3, the stronger the activation of the attentional control system, the better the decision-making performance. So what do we mean by decision-making performance? So, this is, they set up this multi-arm bandit task, or arm bandit task, which is how they claim is their simplified model of wider control effects of interest, what they wanted to monitor. And so each bandit has a mean reward that changes on each trial, but the subjects aren't told that the change is happening. They have to learn by active sampling. And then each trial itself is classified as either explore or exploit, shift versus stay. And they are selecting the bandit they want to choose in order to maximize the reward over a trial. The 300 trials, it's divided into 4 sessions, and yet the performance is estimated totally by total amount of points after all trials. So one thing they have in the methods here is each trial is classified as exploration and exploitation. Do I explain a bit? No, okay. And what happens is they say, if the participant shifts back to what's currently the best performing bandit, according to what they know, they would class this, or no, any shift from one bandit to another, they would class it as an explore trial. And when you select the same bandit again, and your last is the same as the last trial, so on each time step, if you select the bandit twice, then because they're the same, this is classed as an exploitation trial. Can anyone think of anything maybe slightly potentially problematic with defining like this? Yeah, Harrison?
You might try the best one and then be like, oh, I'm going to explore now, and then explore for another one, and then go back to the one you know is good, and then go to another one that you haven't visited yet, and go back. And you're exploiting because you know that's the best one, but it is different from the ones that you back. Right?
Exactly, yeah. It's that transfer back as well. If I'm on a task and I go, okay, no, I want to exploit what I know is the best, I'm going back to the one that I think is the best, they would classify this as an explore, when actually you're going back to exploit. So there's a potential thing that I noticed when I read that I wouldn't slightly agree with. So here's what they were presented with in the scanner. They had 4 bandits and they had 4 buttons to press. You have a presentation. We'd have a response time to select. So here they've selected the bottom left, and then a numerical reward would appear. And they would do this continually. And then it's during the trial shifting procedure, the levels that each bandit represented would slightly shift. So you kind of have a mean normal distribution around it. You start sampling around there as well. So it's a very noisy estimate of which is the right decision, and it means that you can't always rely on exploring and exploiting, because this everything becomes jumbled up again, and you have to kind of start again and constantly update what you believe are the best levers to pull. So what they found was when you look at all of the exploitation tasks over the exploration tasks, you see a lot of activity in the medial prefrontal cortex, and this is claimed to be supporting the dopamine reward system. And the choice to maximize the best possibility is seen as, so you can see here that it's the hippocampus and the ventral medial prefrontal cortex is highlighted here, which are basically the reward system. And this is when you want to exploit, you're consistently concerned about, what is the reward? So you're monitoring the dopamine level, and this is saying at the start and end points of where there is activity propagating over there. When you want to explore, the hypothesis, I'm not sure if it was hypothesis 2, I think it was, they said that attentional control is more going on as well. You need to sort of override the ability to want to just maximize the reward because you're considering alternative possibilities. They also found activation in the insula. Does anyone, it's on there already, but does anyone already know what the insular part of the brain is typically implicated in? I can just tell you not to look at that. I'll just tell you it's fear. So one of the things they claim here is that if you are so focused on a goal and you are taking some uncertainty, there's a level of underlying anxiety or fear in terms of not knowing, and this is what's triggering the activation in the insula. I'm not 100% sure I believe that, but that's what they claimed in this paper. But basically what you can see is in terms of the 2 contrasts. So basically what's going on here, one second, sir, is the difference between the tasks is so similar. They're just pressing the button and defining on a shift or a stay. And the networks that you find afterwards are just so different that I think there is something else going on. And this whole attentional control thing, I think, is a promising avenue for what's actually going on here. Yeah, Harrison?
Is the NCO strictly associated with like fear and anxiety, or is it like the reverse inference thing?
I'd say, yeah, you're right in terms of being able to spot that. It's like, it wouldn't have been part of a hypothesis. They found, what it's associated with, and then they tried to mix it into the conclusion in the end as well. So that's very well spotted. How much time do we have? We have 10 minutes left. Okay. So the brain is an actor-critic model. So section 15 of the Sun and Barter book goes into a lot of the neuroscience concepts. And one of the things that has been quite influential in that work, in terms of what they picked up on as well in the wider field, is that if you consider the reinforcement learning model of actor-critic, we have an actor which was selection action, and then a critic which monitors the rewards, reward prediction errors, and informs the actor of how to perform better. So I'll just read this here. Neuroscience is still far from reaching complete understanding of the circuits, molecular mechanisms, and functions of the basic activity of dopamine neurons. But evidence supporting the reward prediction error hypothesis, along with evidence that basic dopamine responses are reinforcement signals for learning, suggests that the brain might implement something like an actor-critic algorithm in which temporal difference errors play critical roles. So typically, in terms of delineating what part of the brain is designated as the actor or the critic, it's all to do with the striatum, which we saw is this big structure before that contains the nucleus accumbens, caudate, containment, etc. And so we have the dorsal striatum and the ventral striatum. One is active, one is critic. And so this is the proposed model for how the brain is an active-critic model in terms of, on the left we see the reinforcement learning delineation, and on the right is the brain as well. So on the left we have this temporal difference error, which is this delta that feeds into the critic and the actor model. But in the brain one we have the VTA and the substantia nigra, which is where dopamine is produced, and this is then the temporal difference signal in the brain, which feeds into the ventral striatum. So yeah, this is the critic and then the actor is the dorsal striatum here. So this is the model of, as the environment will feed in information through the cortex, this system looks to be quite promising in terms of mapping out how the brain might actually be implementing one of these algorithms. But so the actor-critic algorithm is model 3. And if you remember, the actor is supposed to be in the dorsal striatum. There's been some recent research in rats that actually said the dorsolateral, so lateral means side and medial means in the medium. So if you can imagine, say, one of the brain's hemisphere, you have the outside that you can see and you have the medial side which you can't see. So if we look back at the actor, which is supposed to be the dorsal striatum, and we think of the brain as an actor-critic model, which is model 3. There is some more research that says actually the dorsolateral striatum is more connected to model 3 reinforcement learning, whereas the dorsal medial striatum is more like model-based RL. So there is a bit of a difference here. There's quite a little bit more to the story. And for that, I'm going to leave that to Thursday's paper, which is states versus rewards, the dissociable neural prediction error signals underlying model-based and model 3 reinforcement learning. So there's lots about the intraparietal sulcus, the left prefrontal cortex, ventral striatum, reward prediction errors, and how the brain might actually have these links to both model-free and model-based RL. So the outstanding questions to consider now is how reinforcement learning is modeled in the brain. It's at this very kind of small level where we take a lot of inspiration from monkey research or rats, and we do a lot of these recordings which are typically considered unethical to do, except in the very rare cases where there are medical interventions that need to happen. So what happens on a larger scale? We just can't really seem to find a good way to measure that. Maybe we shouldn't be measuring it at a larger scale until we've worked out some more of the basics at the beginning. But then what about feedback on action given after a week? Let's say you're at your job and you've sent up a proposal to your manager, for example, and you won't know until your monthly review at the end, whether that was actually a good thing to do or not as well. There's no sort of current model for how we can model things after this time, and what is controlled after a week and where is that stored. There's the actual implications for how we learn and have reinforced signals back again can only really be done in this kind of huge stimulus basic reward, where we can measure these things on seconds and afterwards as well. There's clearly something else going on in the reward prediction system that is beyond current knowledge at the moment. And And also, how readily can we apply animal models over to humans? We're not 100% sure. There's a lot of reason to believe that it's a good and promising method to do that, considering how much, say, DNA we share with, say, chimpanzees and other animals. But then also the measurements are that we can make in non-invasive recordings are, do they give the right granularity as well? Is it enough to look at these kind of broad blobs on the brain and say that's the attentional circuit? That specific network of activity is monitoring reward, and it could be a bit too granular to we need more granularity in attempts to be able to make those decisions. Otherwise, we kind of fall prey to the potentials of reverse inference, like Harrison pointed out. If you want to learn any more about this, there's a great series on YouTube called 2 Minute Neuroscience. They have a whole section about like 150 different videos, but videos 14 to 22 are all connected to dopamine system, Nucleus Accumbens, and all of the brain areas we've mentioned so far today. We also have quite a few good YouTube lectures on basics of reinforcement learning in the brain. There's also some very good basic tutorial on basic reinforcement learning that was presented in the Amy Slack recently as well. So I put the link here. I'll put these slides in eClass afterwards, so you'll be able to click those links as well. Also check out chapter 15 at Sutton Bartlett of the neuroscience chapter. And if you see anything online by Matthew Bopnick, he's at DeepMind UK and does a lot of these kind of computational approaches to reinforcement learning, as well as a ton of other interesting things. And that's my last slide. Does anyone have any questions or anything, any observations, anything to bring up? Nobody? Yeah?
I guess
No, go ahead first.
I was gonna say we're kind of going past, but I get that like the dopamine is the reward prediction error. What is the reward? Like, is there a reward?
The reward can be quite abstract in terms of, often for, say, monkeys, it's like a little shot of juice that would come down, or it's like it's cheese for a mouse or something. It's like it's to the individual as well, which is sort of what you see when you can change the value of what a reward means to the specific animal, whether it's money for a human or not. It's just anything that it's not just a single unique thing, that it's a very generic concept of something that's the gives pleasure to the animal. For it could be food, money.
Yeah, I was just confusing the where they predict one and they receive one. The reward prediction error is 0, but I was just wondering like what's in it for them. Like,
also, they're not predicting one. This is just how the reward prediction error would model that. So that could easily have been a bell signifying that you would get cheese, or have some symbols together and a shot of juice as well. So the whole idea of 1 and 0, it's just that the actual abstract value of what the reward is, where I've said 1, that could be anything as well. This is just in a kind of modeling framework where if you look at the old, like say, backpropagation rules in terms of, you just take the sign. So like the early multi-layer perceptrons, it would just be that you move 1 down and up. And then it was only after that people started to say, no, we want to do it we want to move the weights in the direction proportional to the gradient. But before then, it was just kind of like 1, 0. So that was just how it's a good pedagogical tool to represent.
Just in relation to the second question on the previous slide, is there like not a current theory in relation to like how memory acts in things, whether or not memory could like give the same type of input to those neurons?
Memory research is like some of the most messy I've ever seen. It's so difficult. I think that back in the 80s, people thought that we would have solved this by now. Like, what's your opinion on memory research in terms of like, do we have a consensus theory, or I just feel like, yeah. So I think
that's so hard to answer because we have no idea how those mechanisms might ever.
Some sort of things can be implicated in terms of that, but in order to make some sort of prediction you'd be confident wouldn't just mess up your entire experimental paradigm, I'm not sure. But that would be the issue to say solve. And obviously this what happens after a week, for example. Obviously your predictions are stored in memory and you want to go back because you need to remember what you've done and what led to the potential good or bad feedback. So memory is definitely in there as something, but I think the scope for one set of studies to be able to have a consistent, well-considered theory to encompass that is still quite far away in the future.
You need it to be like really, really fine grained to see what's happening almost at the neural
Or at
level.
least to have a slight glimpse into something that's very repeatable that might, be in a very small part of the system that you can test.
It's hard because as soon as you repeat it, you're going back into the memory. It's causing issues with your test again.
Yeah. Exactly. What time is it now? Is it 25? Yeah. Okay, well, thanks very much for today.